I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking today with Gary Stephenson, aerospace engineer and STAIF Conference contributor. Well, first of all, I want to thank you for doing this interview. I should tell the audience that you've been working diligently in the background on a number of breakthrough gravity-related concepts for years now, and it's taken a bit of coaxing to finally get you to agree to an interview, but I think it's well worth the wait.
Thanks, Tim, for the introduction. It's an honor to be called upon for an interview by you.
Well, in this case, the honor is all mine. The work that you've done has just been tremendous, and it's really, in many ways, been recognized in the STAIF conference. But it's great to finally get you on tape.
Thanks, I appreciate that.
Well, let's start with a bit of analysis. I did an interview with Eugene Podkletnov last year on the subject of his new force beam experiment. As you know, this experiment essentially consists of a multi-gigawatt pulse from a Marx generator across a stationary set of superconductors, which he claims produces beams of hundreds of pounds of force, which crush brick and warp metal like hitting it with a sledgehammer. You've actually described a theoretical framework for Podkletnov's claims in a 2005 STAIF paper on the Gertenstein effect. Can you describe the effect for us and how it may explain some of the claims that Podkletnov has been describing?
Sure. Yeah, I've heard similar rumors about Podkletnov's claims. We haven't seen anything in terms of video or anything, unfortunately, yet, but I think you're referring to his second experiment, the impulse experiment. Is that right?
Yeah, the claims were just tremendous. I'd been under the impression that he was only getting maybe around 20 pounds of force, and it turns out that it was considerably more than that. He's claiming hundreds, so it's a real breakthrough.
Right. Yeah, just for the benefit of the audience, in terms of background, there's two main experiments Podkletnov has made claims on. The first was this rotating superconductor that, when placed in a magnetic field, would lose some 3% of its weight. Of course, that's been tested by NASA and by others in England and in Canada, and no one has seen any effect. So that one has been pretty much ruled out, at least with experiments to date. But this impulse experiment is the second one you're referring to, and that one has been difficult to duplicate only because he has not been very forthcoming about the experiment. But what made me curious about it was the configuration of the experiment was essentially he's zapping this giant lightning bolt through a fixed superconductor. Then he gets a gravity wave out. So he's putting electromagnetic fields through a superconductor and getting gravity waves out. What made me curious about this was it's somewhat analogous to the Gertenstein effect. The Gertenstein effect is an effect that was discovered by a Russian physicist working with general relativity. This is not any new theory, but is straight out of Einstein's general relativity. And what it states is that there can exist a synchro resonance between electromagnetism and gravitational waves in the presence of a magnetic field. So he published this in '62 only because it was of astrophysics interest to the general population, and not much was done with it. Then Portia and others came along later on and tried to do a better job describing what kind of a gravitational wave would come out of this. And so he has done further work in that area. So the reason I thought this was analogous to Podkletnov is because superconductors can have a supercurrent in them and then can therefore create a magnetic field. If electromagnetism is placed through the magnetic field, it is certainly possible, according to the Gertenstein effect, to see a gravitational wave come out of it.
Well, the Gertenstein effect is raising a number of eyebrows. I mean, it's actually a real breakthrough that you've been able to dig up. The other day I had Dr. Eric Davis on the phone, and he actually described that as a preferable explanation, as a first-order effect, than some of the unified field theory work that we've been talking about lately. So it's definitely...
Yeah, there's been a number of approaches in trying to describe how this might be theoretically possible, and so the Gertenstein effect is certainly one of those possibilities.
Yeah. Well, I had an audience question, and I simply couldn't resist asking this one. Essentially, the person writing was wondering if the gravitational coupling in superconductors with the B field and E field at right angles produces a true third vector field, or if the third vector is actually in line with one of the other field vectors, but at right angles in maybe another dimension.
Yeah, that's kind of a technical question to address in a radio interview. I'm not an expert in superconductors. I can say that the Gertenstein effect itself when he was working with it, was a free space solution. In other words, when he solved the general relativity field equations, he did so for free space. So in the free space solution, if you look at a transverse electromagnetic wave, this is a wave that's traveling transverse to its electrical and magnetic axes. In a case like that, the B field, or the magnetic field of the wave, needs to be co-aligned with the static magnetic field of the Gertzenstein effect. The Gertzenstein effect field would just be a strong magnetic field that would be co-aligned with the transverse part of the wave. In other words, so this TEM wave would have to go at a right angle through the magnetic flux lines. And if you oriented it that way, then along the direction of motion of the EM wave, out would come a gravitational wave. That's the orientation.
Oh, so the gravitational wave...
And Portilla extended that solution to traveling through matter. And he did a sphere as one very simple case of an EM wave going through matter and also being exposed to a magnetic field. And his solution, when he finished all the math, was a kind of a Bessel function distribution of a gravitational wave that came out the other end.
So the gravitational wave is actually traveling the same direction that an electron would be, right?
That's right.
Interesting.
Well, as the photons that compose as the EM, incident EM, light wave or RF wave.
Oh, sure. Well, the work of Poglavinoff, Ningley, Bob Baker, and many others falls into a category that we generally call high-frequency gravity wave technology. Many of these technologies rely on superconductors, but not all of them. I was wondering if you can give us a bit of background on the HFGW technology, maybe some of your top picks in this area.
There's actually two broad classes, and I have to say it's not actually really a technology yet. It's sort of an emerging technology area because, of course, we have yet to actually measure gravitational waves on Earth, and so it's still a bit of a challenge to create these in the lab. There are a number of plans on paper to do gravitational wave generators, so I didn't want to mislead anyone out there into thinking that, yeah, we're playing with these every day or anything. But there's a good body of work that has been published in terms of theoretical applied physics in these areas, and so I can share some of those with you. The two main, in terms of gravitational wave generators, two main areas. One is synchroresonance. This is creating a gravitational wave through resonance with an electromagnetic wave. And I just described one synchroresonance technique, that'd be the Gertzenstein effect. There's another one that an Italian Professor Fontana has described called the Gazer. This is a gravitational laser. And this could theoretically occur in a semiconductor or superconducting transition, which is a spin-2 transition. And his theory is a quantum mechanical theory, and he argues that the spin-2 transition would then essentially be gravitons, and that those gravitons would be emitted at the same frequency as the incident signal that's vibrating back and forth within the regular laser. So those are two synchroresonance techniques. Then there's a whole other class of these rapid mass energy fluctuations, and this is Dr. Baker's area, and Dr. Woods has also done some applied physics in this area. And this area is where you have a third derivative of motion. In other words, a change in acceleration is what's important according to standard gravitational general relativity. And if you get this third derivative, you can get a gravitational wave coming out, and the power goes as the third derivative. And the good thing about the second technique is it's a nonlinear scaling with the frequency of the wave. Hence, high frequency would be a significant advantage because there's a huge coupling loss between mass and energy fluctuations and a gravitational wave. So how do you overcome this very, very poor coupling? Well, one way is with an enormously high frequency, and then you start scaling that exponentially, and then suddenly you can overcome this poor coupling.
Sure. Now, in some ways, Baker's work, I actually, the best mental picture that I guess I can draw is hundreds or thousands of little piezoelectric transducers all moving synchronously from a microwave projector.
Yes, that is one technique, is he impinges, somehow produces rapid mechanical motion. For instance, in piezoelectrics, or simply by striking a mechanical object with an X-ray laser or some other powerful energy source. And if you do it quickly enough and in a way that's synchronized, you can produce a collective effect that's extremely large, at least at very short time scales.
Sure. Now, one of the interesting things that Tony Robertson had mentioned was that this same effect might actually be occurring inside the lattice vortices in superconductors. So there may be a mechanical effect as well as the synchronous effect going on in some of the stuff that perhaps Pogklanoff or Ning Li is working on.
Yeah, I'm not familiar with that aspect. Certainly, that's one speculative area that's certainly possible.
Well, one of the fundamental assumptions about the high frequency gravity wave devices is that they produce something called a quadripolar wave. Basically, this is like a ripple in space that doesn't exactly correlate to the propulsive effects that we've been hearing about. In essence, to make a high frequency gravity wave into a propulsive force, you need to rectify it, right?
Yes. Essentially, what we're talking about here is conservation of momentum. It's impossible to create a transverse gravitational wave that's simply a simple sine wave like you would see with an electromagnetic wave. And the reason for that is conservation of momentum. You wouldn't see momentum conserved if such a wave could exist. So the lowest order solution that you can have with a gravitational wave that conserves momentum is a quadripolar wave. And it's a little bit difficult to picture what a quadripolar wave would look like in terms of a space-time ripple. So the way I like to describe it is by what it would do when it's traveling through space-time. So, for instance, if you have a cross arrangement of four test masses in space-time, and you have a gravitational wave pass through the center of a cross that has these four test masses, one to the left, one to the right, one up and one down. Then, for instance, during one phase of the quadripolar wave, the test masses along the long axis of the cross, the top and the bottom test masses, might be pushed away from each other by the wave. At the same exact time, the test masses on the left and right would be pulled towards each other. And in this manner, there's momentum changes on all four test masses, but they cancel each other out. And in this way, momentum is conserved, and this is why it is possible for a quadripolar wave to theoretically exist in terms of space-time ripple. Then on the opposite phase, the test masses along the vertical axis would be pushed towards each other, and on the horizontal would be pushed away from each other. Is that making sense?
Sure. I'd always envisioned it a little bit. This is a weird example, but I always envisioned it a little bit like a gummy bear, where if you squeeze the tummy, the ends kind of bulge out.
Yeah, that's another good example. Or you push on it, and the tummy squeezes out. Either direction, either example is a valid example. And of course, the problem with that is then it's a perfectly symmetric effect, and so there's no way to obtain any useful work out of it unless you rectify it.
Well, but one of the things that you've been working on is actually a new theory that may suggest self-rectification, right?
Yeah, I had been struggling with this a little bit because the way that I think I provided you with some material that you published on your website in terms of quadrupole rectification that would work with the fluctuating mass energy. This would be using one of Dr. Baker's techniques, third derivative change. And if you had such a quadripolar wave generated that way, you could have a very asymmetric waveform that would be very strong or very fast change in one direction of the masses, and then you would do a very slow change in the other direction, and that would essentially rectify your quadripolar wave, so that it was always kind of scooting. More coupling was happening in one direction than it was on the return trip, or in the other direction.
We've actually...
That would be one way to do it. Unfortunately, that technique does not apply to synchroresonance. In the synchroresonance techniques like the Gertzenstein effect, something I had overlooked previously, that doesn't apply because in synchroresonance you have to have a symmetric waveform in order to obtain the resonance effect. At least that's the fear. So is there another way? I was casting around for another way to achieve gravitational wave rectification. Well, as it turns out, that problem had already been solved about 14 years ago by a Greek, and I'm probably going to slaughter his name, Dimitrios Christodoulou, I think is the way to pronounce it. It's Christodoulou. And he teaches at Princeton. He's also taught recently nonlinear general relativity in Zurich. And in '91, he discovered something called the Christodoulou memory effect. And this memory effect states that if you have a rapidly enough changing gravitational wave, that these test masses I was talking about don't return to their original location. They continue to be scooted along in a way that makes it appear that there's a Coulomb-like force, is the way that Kip Thorne described it. Kip Thorne has described this memory effect in '91, as well as Fraundiner, a German working in Munich. All of them pretty much describe the same effect, this memory effect, first discovered by the Greek.
But this is almost a hysteresis effect,
this is
right?
one way to achieve rectification without the use of an asymmetric waveform.
Now, this effect is, in essence, kind of a time-space hysteresis, right?
Yes, yeah, it's a hysteresis effect in that the space-time structure, the fabric of space-time, does not return to its original state. It has some memory. That's why they call it the memory effect, Christodoulou memory effect.
Sure, sure. Well, one of the areas that I'd like to ask you about is the scale of these effects, because oftentimes we assume that breakthrough science is going to start small and eventually work towards larger projects.
Right.
Again, Pogplanov is using the highest power levels, with the Marx generator-driven project running well into the pulsed gigawatt range. However, I also have a few other examples. Fontana and Baker in 2003 predicted a 10 megawatt pulse output, and Baker, in a solo paper later on, also suggested a different method to produce a 380 kilowatt effect in continuous power mode. Now, Ning Li has actually made claims about generating the 11 kilowatts of power that she predicted earlier in 2003, and Baker and Li together derived a theoretical approach to focus power levels in a confined area to an enormous 10 to the 19th watts per square meter. I'd just like to get your thoughts or opinions on output from these devices, as well as maybe an educated guess as to what the conversion rate or efficiency might generally be.
Right, yeah, we have to be a little bit careful here because there's two different powers at work. There's an instantaneous power, which can occur at very low duty cycles, and then there's this continuous power, which is the kind that you would need for propulsion. Most of the experiments that are being designed right now are pushing for very low duty cycle, very high instantaneous powers. Because of the poor coupling, we need that kind of a thing just to be able to sense the gravitational wave. So I don't want to sound negative or discouraging. I think this is a very interesting field, and I want to encourage people to work in it. But it's very, very poor coupling. We're talking about coupling like 10 to the minus 40th are the sorts of efficiencies that we're looking at, simply due to the way that mass energy couples to gravitational waves. Now, there may be more efficient ways to couple, and certainly this assumes linearity, and like I say, many people are working now with the nonlinear aspects of general relativity. So there might be something there. But for instance, the 10 to the 19th watts per square meter, these are created over the course of femtoseconds. So you can start out with only a watt or so, or tens of watts, but if it's only for a femtosecond, then it looks like, when you're dividing by that small period of time, it looks like an enormous power in terms of watts. But the continuous power one's a little bit surprising to me, the one that Ning Li had been quoting. I don't know where that number comes from. The other thing to be careful about here is the 2003 paper is by Baker and Li. That's a different Li. That's Fengyu Li in China versus Ning Li that's here in America.
Oh, okay. Well,
two different Lis.
You attended the STAIF 2005 conference, this year's conference, and it's rapidly becoming the premier conference for gravity research. From what you've said so far, this is an excellent venue to attend. As I understand it, the rectification idea resulted from a presentation at that very conference.
Yeah, that's right.
You'd also mentioned Paul March and James Woodward. Can you give us an update from some of the notable info they published at STAIF this year?
Sure. The March and Woodward data I'll go over in a second. But getting back to STAIF 2005, I wanted to thank those guys for hosting us. This is a group of fairly regular folk. That originally this conference was geared towards the Center for Space Technology Applications International Forum, and it was a way to draw the international community into a conference having to do mostly really with nuclear power in space. For instance, nuclear thermal propulsion and nuclear electric propulsion, thermionic emission type stuff. A number of different technologies that are by our standards pretty routine. There was also some interesting things on fusion this year, inertial electrostatic confinement, which I think grew out of the Farnsworth Fuser type of work. But these are all nuclear technologies that are also part of that same forum, part of that same conference. They're more mundane in nature. But a few years ago, they started allowing a futures conference, and this is the one that has the alternative propulsion concepts. And it's been a great venue because after the kind of the demise of the NASA Breakthrough Propulsion Physics program, we haven't really had a venue to air these new ideas and to publish some of these new ideas. And so it's good that they've allowed us the space to do that at STAIF. So my kudos to them for allowing us to do that. One of the interesting ideas that you brought up here was that of James Woodward's. Hector Brito, the Argentine researcher, also has come up with a similar approach. These are a class of thrusters we'll call Machian drive thrusters. These result in momentum transfer to the space-time fabric itself. That's the concept, at least. And there are some test devices that James Woodward and Hector Brito and now Paul March have been working with over the years. All three of them have gotten, although they're very small, they are measurable and they are repeatable, and they seem to be valid result in the area of these Machian drives, these momentum transfer devices. They're very small. They're like nanogram type thrusts or micrograms at the very most, but still they are measurable, and so it's an interesting area that I think we should continue to pay attention to.
Absolutely. As I understand it, they're well into the area beyond experimental error or deviation.
Oh yeah, yeah. In fact, these are of course published in the STAIF proceedings, and I think I've described at least at a very high level in my meeting notes that are published to your website.
Yeah, we do have those up, and I want to thank you for providing them because I missed the conference.
Sure, my pleasure. It helps get a broader audience to the STAIF 2005 conference, so I'm happy to do that.
Absolutely. Well, there was another presentation at the conference this year, which was about Heim Theory. This is one that I've put some research into myself. I need to do more on it, as it seems to validate some of the ideas relating to anti-gravity effects in Einstein's unified field theory. This isn't surprising, as from what you've said, Heim theory is another derivation of Einstein's UFT. But what is surprising was the backstory involving post-war German research by Messerschmitt. Can you tell me a bit more about this?
Yeah, now Heim was a post-World War II theoretical physicist that kind of worked in isolation, and he approached it from, most unified field theories are approached from the quantum mechanical perspective. His approach was taking it from Einstein's geometrification of space-time and quantum theory. So he approached it from Einstein's direction, from the general relativity direction. So he generated this theory. It was written in German. No one knew what to make of it. There are good and bad things about the theory. The good thing about the theory is using geometry and first principles, a few simple assumptions, he was able to derive the masses of all the elementary particles. This is still a bugaboo in terms of theoretical physics. Why do all these particles have all these different masses? And so anyone that can do that, obviously this unified field theory is of general interest. Another interesting outcome was there are three types of gravitational force, not just one. So it could account for some anomalies seen with dark matter and dark energy. And so finally, he described as part of this and predicted some coupling to one of these types of gravity between electromagnetism and one of these types called gravitophotonic gravity. So these are some of the interesting features. Some of the negatives, at least negatives from the point of view of physicists, is that it included quite a lot of metaphysics. So his theory has, I think, and I'm just going off memory here, something like 12 dimensions. The 4 ordinary space-time dimensions, then there's 4 probability distribution dimensions that kind of describe evolutionary processes and stochastic processes in the universe. And then there's 4 information, he calls them information dimensions, that really he describes in a sort of a metaphysical context that information itself exists and has an existence all of its own. So these kind of 8 add-in dimensions are a little bit troubling to physicists because they describe more than just physics, right? They're describing life processes and evolution and the growth of information and so on. And so no one really knew what to do with this stuff. There were a number of researchers that were intrigued by the coupling between electromagnetism and gravity. Apparently, according to the presenter this year, Professor Joachim Hauser, he said that one of the groups that were working on with this theory were at Messerschmitt in the, I think it was the 60s. This is secondhand, just based on Professor Hauser's presentation. And that this Messerschmitt group, when there was a merger with Daimler-Chrysler, then they didn't really know what to do with these physicists. And so I think at that time they disbanded the efforts. I think this was like in the 80s time frame. Now, of course, Daimler-Chrysler has even been merged once again into an outfit called EADS. This is a European defense contractor. And once that occurred, I believe at that point the decision was made to release all of these research papers. And so that's why we have suddenly this new information and these translations into English. And so I wanted to thank the professors working so diligently on this that had translated this, because now this opens it up to the rest of the world, and the rest of us get to find out quite a lot more about Heim's theory.
Sure. Well, it seems like, Heim theory having 12 dimensions, and then I've heard Einstein's unified theory being described as kind of a primitive form of string theory. It seems like the string or newer brane theories may actually be leading us towards new types of couplings between gravity and electromagnetism. So,
It's certainly possible. It's the UFT type theories are well beyond where I'm working. I work more in the applied physics area, so I'm just going to have to leave it to the theoretical physicists to sort that out. But it's certainly an interesting it's an interesting theory, and it makes results that should be measurable with powers and field strengths that are within ranges that are achievable. For instance, rotating magnetic fields of some 25 Tesla should have measurable effects on gravity. And so if this is true, we should be able to measure this to confirm or disprove Heim's theory. So it's nice when it has predictive power like that.
Absolutely. Well, let's close with your contact info. Can I get a web address for your company, Seculine Consulting?
Sure, Tim. I don't actually have a URL, but I do have an email address.
Oh, okay.
It's seculine@comcast.net. It's spelled SECULINE at Comcast, COMCAST.net.
Great, great. And that's probably the primary way that people can get in touch with you.
Yeah, that would be the best way to get a hold of me, since this is something I'm really just doing in my spare time at this point. But it's been a lot of fun, and it's been very rewarding work, and I would certainly encourage others to become involved in gravitational wave theory.
Absolutely. Well, even as a spare time effort, you're still doing remarkable work, and that leads me to
Thank you.
That leads me to my final question. Any ideas on what you'll be presenting at STAIF 2006?
I don't know, Tim. I've signed on right now only as a co-chair, and a part of that co-chair effort is to gather in papers from new authors. So this is my chance to plug STAIF 2006 and let the authors out there know, potential authors know, that if you have any ideas in the gravitational wave area, You have my email address. I'd be delighted to review them and hopefully include them in next year's conference.
Wonderful. And again, that's seculine@comcast.net.
That's right.
Well, thanks again for your time, Gary. Have a wonderful
Thank you.
evening.